All right, without any further ado, I hand it over to Connor.
Cool, thank you, Michael, and thank you guys all for attending my final seminar. Today I'm going to be talking you through the sort of last 4 years of research on my thesis, which I've titled Beyond Place Matching for Visual Place Recognition on Robots and Autonomous Vehicles. I'd also like to start by acknowledging the Turrbal and Yagara people as the traditional custodians of the land where QUT currently stands. Now, I probably don't need to tell most of you that robots and autonomous vehicles are starting to pop up and become sort of more widely adopted, sort of in environments where we see people and starting to coexist with people. And so we see this in applications like mining, passenger autonomous vehicles, defense, agriculture, and even service robots. And so because we're starting to see this integration of sort of people and robots, safety is becoming a critical part to ensure the continued protection of both people and robots in these applications. Now, two of the key behaviours which are relevant to this thesis, and I'll be talking about today, are the localisation and scene understanding capabilities of these robots. So I'll start with a little bit of an introduction and primer to these two topics to get you in the right headspace. So localisation is the task in robotics of determining a robot or a platform's location within its environment. And so usually this is done through sensors such as IMU, GPS, LiDAR, and radar. Now today I'm actually going to be talking to you specifically about the task of visual place recognition, or VPR as I'll refer to it as, which is the task of doing this, an approximate form of this localization solely using cameras. And so given two images from the same place, can you tell that they are actually from the same location? And the second part in robotics literature, which will be relevant to this thesis, is scene understanding. And so this is the general task of determining what and where there are particular objects in your robot's environment. And specifically, I'm going to be talking about semantic segmentation. So once again, this is the task of doing this scene understanding using images only and trying to get a pixel-wise set of object labels to use throughout an image. So where does this all sort of link into the thesis and the main concept that I explore in this research? Well, we started with the main idea of how can we build frameworks and priors around these existing VPR place representations to improve the functional performance both within VPR and other robotics tasks. And so this involved a couple of key components throughout the research. So first of all, determining what information can we actually yield from these powerful place representations. And then, of course, how can that actually improve the functional utility of sort of methods in robotics? This can be both VPR and non-VPR related. So I'll start with a little bit of an overview of how I'm going to run today's final seminar to give you guys an idea of what's coming up. So I started with a bit of an introduction into the topic. I'll then proceed into a bit of a deeper literature review on the fundamentals and state of the art in visual place recognition, semantic segmentation, and then a couple of points sort of highlighting what we're trying to achieve with this thesis, where things like location and VPR is already used in non-typical or non-localization tasks. So I'll start with the first contribution, which looks at how we can use VPR in semantic segmentation to improve performance in challenging conditions. The second contribution looks at how can we improve on an existing VPR method, which is multi-process fusion through the prediction of complementary VPR approaches. And then the third contribution finishes with showing how can we use VPR place representations to modulate the sequence length used in VPR, all with the goal of consistently exceeding some nominated minimum performance. And then I'll wrap up today with a bit of discussion and future work around limitations and how I think the research in this thesis can give the field some opportunities going forward. And with that, I'm going to get into the literature review for the visual place recognition component of this. So I'm going to discuss sort of how we perform localization with VPR, how a place is actually represented, and then given two images, how can we actually tell that they're from the same location? So the general methodology that we adopt in VPR is we have an environment which is represented as a topological map of images. And so usually the assumption is that you have a sequence of images which is sort of related sequentially throughout the environment. And then we have the job of, given a query image from the current location of a robot or a platform, can we match this to a reference image in this database of images that we already have? And these reference images are usually geotagged, which is what allows us to do this approximate form of localization. Now, how we actually match these images together is we form representations which become abstract vectors of these places. And so given that we formulate the VPR task as a image-only task, this brings about three sort of core challenges that are usually persistent across literature. So we have things like appearance changes between our query and our reference images. So this can come in the form of illumination, weather, or urban development changes. You can have things like viewpoint variations. So you're actually looking at the same place from a different viewpoint. And then what could almost be considered like the opposite of these problems, where you have geographically separate places that don't correspond, but actually do look similar under certain conditions. And so how literature usually addresses these problems is we try and form these place representations, which we refer to as features or descriptors, which actually become robust to these different challenges. So broadly, these can be separated into global and local features, where global descriptors capture the general image structure of a place. And so because we're looking at a generalized structure representation, this allows them to be more robust to appearance changes, but are a bit more sensitive to viewpoints. And so traditionally we can handcraft this with some of the methods I've listed here. And then the complement approach, the local feature approach, is sort of a two-part process where we identify key points in an image which allow us to recognize it, and then we look at particular characteristics around these key points, such as gradients across pixel intensities, which allow us to form this place representation. And so this then becomes robust to viewpoint because we're looking at key points, not a general structure, but it can be sensitive to condition variations, which can change the key points we actually extract, and it's a bit more computationally intensive. And so some of the seminal works in this traditionally have been things like SIFT, SURF, and ORB. But more modern approaches introduce the use of deep learning. And so this is through things like neural network architectures, quite popularly the convolutional neural network, or CNN as I'll refer to it going forward, where there's been extensive research which allows these deep learning frameworks to extract feature vectors which are robust to both appearance and viewpoint changes. And so there's other components that we looked at, such as middle layers are more robust to appearances and top layers are more robust to viewpoint changes. And so what we can actually see in literature is that these neural networks have been used to both develop global and local descriptors, and descriptors that are overall more robust to all the changes that we see in visual place recognition. And of course, with the downside with these deep learning architectures, they do require a fair amount of data to train to get useful features from them. And so once we have these sort of abstract feature vector representations, how do we know that two images are from the same location? Well, because we have vector representations, we can just use a set of mathematical distances and find the image with the lowest distance in our database. And so this is commonly achieved using things like sum of absolute difference, Euclidean distance, or cosine similarity or cosine distance. And we can actually represent these distances in these structures such as distance vectors or distance matrices. So I'll direct your attention to the plot on the left-hand side. So a distance vector is for a single query image. We find the distance from it to every reference image in our database. And so in this plot, you can see we have the reference image index in our database, and then the vertical value then just becomes the distance to the query that we're actually looking at. On the right-hand side is sort of the extension of this, where we have multiple queries and we're looking at the distance to every reference in our database from each of these queries. And so in this plot, the x-axis represents the query image that we're looking at. The vertical axis, or the y-axis, represents the reference image in our database. And then the pixel intensity is what actually represents the feature distance in this representation. And so now we have all these different methods that I've talked about, sort of traditional and deep learning, and all these ways of looking at the distances from all our reference images. So which is the best approach to visual place recognition? Well, this problem isn't actually as clear-cut as you might think. There's no actual approach that is sort of a best in all scenario situation. The best VPR method can be dependent on the different conditions you're experiencing or the different requirements of your system. And so we have approaches such as NetVLAD, which has decent performance under both appearance and viewpoint shifts, but can fail under extremes. HybridNet, which is a little bit more nuanced, and it actually produces spatially related features, which makes it good in the case of perceptual aliasing, but can fail under even mild viewpoint shifts. We have networks such as APGEM, which doesn't necessarily increase the performance that we see, but does increase the efficiency of our training through the use of a listwise loss instead of the traditional contrastive loss. And then more modern approaches introduce architectures such as transformers to really achieve the state-of-the-art performance where we see from the current state of the field. With the downside to some of these modern architectures like transformers being very difficult to train, requiring lots of data and being a bit sensitive to the actual data that they see. And then, of course, what we can actually do is add post-processing methods on top of these feature extractors that we use. So commonly, there's a couple of approaches which I'll talk about here and are relevant to this thesis. We can use sequence matching, where rather than matching a single query image to a single reference image, we look at a sequence of query images and match this to a sequence of reference images in our database. Now, this is at the, this improves the general robustness of our VPR, but at the additional cost of, as you increase that sequence length, you get increased computation and latency. Now, the other method that is relevant to this thesis is multi-process fusion, and this is where we actually take multiple different VPR methods or feature extractors and combine them together in the distance vector space. Now, this comes at the cost of increased computation and memory requirements from requiring multiple VPR methods, and I'll touch more on this later. So how are these methods actually benchmarked and has performance measured in literature? Well, most research focuses on improving the sort of typical place representation, place recognition metrics that we see on average across a single or series of data sets. And so this is metrics such as precision, recall, and recall at n. But what is particularly relevant to this thesis, and I'll sort of touch on throughout, is that there are a lot of other functionally important characteristics in practical applications that we should be measuring as well. So things like the computation and memory requirements, the localization latency, which becomes important as you increase the speed of your robot or your platform, metrics such as worst case performance, so in the likes of autonomous vehicle applications where safety is an important factor. Even if you have one section in your data set where you have a failure, this can have sort of catastrophic consequences in terms of safety. And then there's alternative forms of research such as introspective failure detection, like can we actually determine when our VPR methods are going to fail? So where does this all fit into this idea that I introduced for this thesis? Well, hopefully I've impressed on you that the current state-of-the-art literature in VPR has these powerful place representations that are robust to a lot of real-world conditions. So where this thesis tries to fit in is rather than improving the typical sort of bold number metrics that you see in a lot of publications, we try and join the smaller amount of research focusing on functional improvements and how can we use existing VPR methods to both improve functional utility of VPR and in other robotics tasks. And so this is sort of focused on improving the adaptability and robustness of robots in general. And so this leads me into the second part of this literature review, which I'll talk about semantic segmentation. Now, I introduced the scene understanding task a little bit earlier, so this can include tasks such as object detection and semantic segmentation, where we are trying to find what and where there are particular objects in our environment. Semantic segmentation is the fine-grained version of this, where for every pixel in an image, we try and provide a prediction of the semantic class of that pixel. And the general methodology that we see in literature for this is we quite commonly use fully convolutional networks. Now this is sort of an extension of the CNN architecture that I introduced before, where we have a decoder component which takes the feature vector and then expands it out to the resolution of the image. And so at each pixel in the image, you have a likelihood that that pixel belongs to each of the semantic classes that you're trying to predict. And then there is more recent works that introduce architectures such as the transformer once again, but I won't touch too much on that throughout this talk. Now, one of the challenges that we see in semantic segmentation is segmentation of images captured in challenging conditions. And so this sort of touches on the task of domain adaptation that we can see. And so a lot of literature uses or trains semantic segmentation networks on daytime or what we're going to refer to as ideal conditions. Now what happens is that these networks often don't perform as well on unseen adverse conditions. And this can be things like night, rain and snow, as you can see down the bottom here in this figure. The additional challenge that you can see pop up in semantic segmentation in these challenging conditions is that labeling these images also becomes a bit less straightforward. And so we see this with nighttime images in literature where you have dark regions in the image where you're not necessarily able to know for certain what the semantic class is, so we label it as unknown. So there are some current methods, or a lot of current methods in literature which deal with this problem. These can include categorizations such as fine-tuning, where you take a network that's trained on a lot of daytime data, and then you just basically continue the training using a little bit of data from your adverse condition on the end. Then there's a category of techniques such as style transfer. Now these can train generative networks to transform the image from one style into another. So for example, night into day, as you can see in the top right-hand image here. And then we've got a category of techniques which I refer to as feature space tuning. And so this achieves objectives such as encouraging domain confusion in the feature space. And so we want features that are extracted from nighttime and daytime images to appear the same in this feature space. And this actually leads me on into one of the approaches where I'll talk about where location information has started being used in this sort of non-traditional space. And so there's a domain adaptation approach which is relevant to the first contribution I'll talk about in a little bit, which uses location information in this domain adaptation problem. And so they use an approach called gradual domain adaptation. And so this uses the fact that it's easier to fine-tune a network through a series of intermediate steps through your domains. So in the day to night problem, if you get different stages of that illumination cycle and fine-tune gradually on each of them, and then they add the use of location information into this. So not only if you use gradual steps, but if you capture the same place under these gradual steps, you both increase performance and you also reduce the labeling requirements of an image. So you can use a sort of pseudo labels because you know that the image in the daytime is the same location that you're looking at through these different cycles. With the caveat that you increase the requirements of you need multiple traverses of an environment to capture these places under different conditions. The other work that I think is really important to show, because it shows the sort of objectives that this thesis has, is research that is using VPR to help the detection of dynamic obstacles in adverse conditions. And so, for example, in autonomous vehicles, if you're driving at nighttime, you can have a set of region proposals and then use VPR to find the corresponding reference place, and this is usually captured in daytime conditions. And then you compare the corresponding regions across these query and reference images and use this to filter out particular proposals. But with that, I'm actually going to jump back into the domain adaptation problem because that is what we target with this first contribution in this thesis. And so what we look at is how can VPR be used in this domain adaptation problem to sort of improve performance and relax some of the constraints on existing methods. And so there's actually two papers that I'm going to talk about here. The first is sort of the main contribution and introduces the key concepts in this first contribution. And then the second paper is a little bit of an extension work that we have on top of this. So the motivation for this first contribution looks at the task of semantic segmentation in challenging conditions from an autonomous vehicle's perspective. So current domain adaptation approaches require both additional training and anticipation of and exemplar data from the conditions that you're going to be expecting when you're out in the world being deployed. And then in the case of the location-based approach that I talked about, requires multiple traverses of an environment to get the training data you need to adapt a network. Now in practical applications like autonomous vehicles, there can be a nearly unlimited amount of these domains. So you have things like rain, nighttime and snow, but then you can also have different combinations of these methods which can increase the number of domains that you must operate in. And so the idea of anticipating and collecting data and labeling from these different domains becomes an almost infeasible or intractable task. And so what we actually propose is that we can use the concept that there are a lot of places in the world that are geographically separate, but actually very semantically similar. So you can stand in a residential street anywhere in the world, and there's a high chance that somewhere in the world, there is another residential street where the road and the buildings and the trees are all in the same place. And using this concept and leveraging existing research in VPR, such as their robustness to these real-world conditions, as I've sort of discussed earlier, we can try and make we can try and improve results in these adverse conditions for semantic segmentation. And so it really leverages the fact that due to research, VPR under these conditions is a more tractable task than semantic segmentation. And the other cool thing that we do in this work is that we take the viewpoint dependence of a particular network, hybrid net, as I introduced before, which is in VPR might not necessarily be considered a top performing method, but we can turn that viewpoint dependence from a weakness into a strength, because it allows us to retrieve these what we call similar places. And so this leads us to this generalized pipeline where we want to use VPR to retrieve semantically similar images from our queries captured in challenging conditions, but we want to make sure these similar places are captured in daytime or ideal conditions. So then when we can use a segmentation of these similar places to bias the segmentation of our query image. And so the way that we formulate this problem is that it requires no additional or domain-specific data or training, and it's framed as a post-processing method, so it's agnostic to the segmentation network, so it can be used with any network existing and can also be used on top of existing domain adaptation approaches. So for the first paper in this contribution that I'm going to talk about, we actually limit the scope a little bit, and so we look at improving just the road class. And so this is partially because in similar places, the road class is quite well suited for improvement via these similar places. And this is because there is particular position and geometric constraints on this class that mean that it's a bit easier to find similar road positions in other images. However, the road class is still a safety critical class and severely degrades in these adverse conditions as I show here. So I think it still represents a good contribution to the field. As a bit of a visualization of the general approach that I described before, you can see here that we start with a query image from our adverse condition, and then you have a reference pool of places. Now again, these are not geographically corresponding to the queries in any way. And we use VPR to actually retrieve the top K most similar places. So in our experiments, I think we use the top 5 images. And so we don't use just the top single match because this sort of reduces the volatility of the times when your top match might not necessarily be the most semantically similar place. And so this is because we're actually using networks that aren't specifically trained for this task, so they are looking for corresponding places, not necessarily semantically similar places. And so we take segmentations of these top similar places and we actually average them out to get this similar place segmentation. Now, if you remember in the literature review I talked about, in segmentation, at each pixel you get a likelihood that that pixel belongs to a particular semantic class. And so what we can actually use is these data structures from the similar place segmentation and the query segmentation, and then use a Bayesian update to produce this refined road segmentation. And so this ended up producing some very good results, as you can see in the top right-hand plot here. What we actually saw is that using this approach across 3 different networks under multiple different conditions, we saw a universal improvement. And this is without data from the target conditions, additional training, or knowledge of the location that we're trying to semantically segment. In the bottom right-hand of the right-hand plot, you can see we actually include a bit of a failure case. And so there are some limitations with this work. I guess first and foremost, we are just looking at improving the row class. And then there is also cases where, even though we try and smooth out volatility by taking the top 5 most similar places, sometimes you're not able to retrieve images that are similar enough to improve performance. And then of course there's the case, well, if your performance is already substantially high, you're not necessarily going to improve it further with these similar places idea. So to sort of wrap up, I guess, what we did in this paper is we were able to introduce the idea that VPR can make the task of semantic segmentation in challenging conditions more tractable by retrieving these similar places. But in order to relieve some of the limitations in this work, we had an extension paper here, which I'm still talking about the first contribution in the overall thesis, but this paper focuses on trying to extend these improvements to all semantic classes. And so we do this by trying to remove the constraint that the retrieved images need to be similar in their entirety. And so we do this by introducing a generation of similar place priors on a patched basis. And so in the bottom left here, you can see we actually use VPR for each patch in an image to retrieve semantically similar patches and then stitch these all together to form our similar place. And then the methodology actually just remains the same as what I described earlier. We also introduce an additional contribution in this work where we look at the entropy of the query segmentation. And we do this so that we're able to sort of toggle when we use our similar places to update predictions. And so we found that in images with high entropy in their segmentations, this indicated that we did need to use similar places to improve performance, and then in images with low entropy, we might not need to use these similar places. Now, unfortunately, the results in this work weren't as clear-cut as the results we saw for the row segmentation. And so the metric that we use in semantic segmentation is intersection over union, which is just a ratio between the ground truth area of an object and the predicted area. And when we actually looked at the mean IOU across all 19 classes, it remains relatively unchanged. Now, we suspect that this is probably because of some of the caveats with this metric, and that it is sensitive for particularly smaller classes. And so when you're looking at road scenes where you have a large variation in class sizes, so there's a big difference between the size of a road and the size of a traffic sign, your mean IOU can be biased by these particularly small classes and your performance on them. So when we look at a weighted IOU based on pixel area in image, which we refer to as looking at the general scene understanding capability, we actually do see an improvement from these patch-based similar places. And so that sort of wraps up this first contribution that I'm going to talk in here. And then we're going to move on to the second contribution of this work. So I mentioned earlier, this contribution actually looks at improving on an existing VPR approach. And so the approach is multi-process fusion. As a little bit of a summary for what I touched on earlier, multi-process fusion uses distance vectors to fuse multiple VPR methods together at the same time to improve performance at the expense of the computation and memory requirements of running several VPR methods in parallel. What I didn't mention last time was that the research before this contribution we're going to talk here actually calibrated the best combination of approaches individually for each data set. And so these few things lead to the motivation of this second work I'm talking about here, where first and foremost we want to reduce the additional computation requirements of this multi-process fusion, and we do this by limiting the approach to looking at the fusion of VPR method pairs. And so we only ever want to fuse two approaches together at once. We then want to introduce the idea of dynamically selecting these pairs to improve the adaptability and robustness of the approach. So in the bottom of this slide here, what you can actually see is we found not only does the best combination of pairs change between different data sets, but also within the same data set. And so we wanted to dynamically predict these pairs so that we can be more robust to these cases. And what we actually wanted to do with this dynamic selection is we wanted to maximize what we refer to as the complementarity of these VPR method pairs. And so what this actually refers to is basically we just want to select the most appropriate VPR method pairing to maximize the chance of successful visual place recognition for each query. And so overall we have a few ideas that we wanted to introduce into the general approach. So first of all, we want to sort of reduce, I guess, the problem by selecting a constant chosen base method, which we use NetVLAD in this work. And then we want to just select the best additional method to pair. So you will always have two VPR methods to pair, but one is going to be a given base method. We then we play around with the idea, as I sort of mentioned earlier, where the best VPR method for localization performance is going to be dependent on the condition changes between query and reference images. And so we use the idea that we can capture this condition change in the VPR place representations and use that to choose our VPR methods to pair together. And how we actually do this is by training a small multi-layer perceptron, or MLP, which is just a fully connected network, to dynamically select these VPR pairs. In terms of specifics, what we actually do is we take the base VPR method, so netbulat in this case, and we take a difference vector between the query and top reference image VPR feature vectors, and we use that as an input to train a multi-label classifier in this MLP. And so intuitively, when you think about it, for each query, there's not necessarily just going to be a single pairing of VPR methods which is going to be successful in place matching. And so we take this into consideration by using a multi-label classification approach, even though at inference time, we just take the single pairing that has the highest sort of logit output at test time. And what we're actually able to find is that we can train a single small MLP model to be performant across multiple different data sets. And how we actually achieve this is we train on partial data from 4 different data sets and then test on completely unseen data from 6. So unseen data from the 4 training sets as well as 2 completely unseen data sets. And we actually saw that we were able to outperform logical comparative approaches to selecting these VPR method pairs. So I'm going to go into a little bit of an explanation on that. If you were to take the training data sets and you were to take the VPR method pair that performs best on average across all of these, this is what I'm talking about in the top dot point here, where I say the best average performing pair across all training data. And then we have a data set specific version of this, where if you separate each of the training data into specific data sets and get the best VPR method pair on each of these specific data sets and use that, we're able to outperform this approach as well. I'm going to wrap up this contribution by talking about some of the interesting findings that we had in this work. So one of the things that I'd like to mention is that the MLP, interestingly, actually learned to choose 3 of the possible 9 VPR method pairs we gave it access to. So in the bottom left-hand plot here, this is actually a plot showing the switching of VPR methods throughout the data set. And so even though it does switch, you can see that it actually only selects 3 of the 9 possible methods that it has access to. And so what we suspect is that the training data we give it, these 3 methods between them are actually able to localize about 95% of the training data, so it learnt that it only needed to use these methods. The other interesting finding we had from this work is that there was typically a dominant VPR method pair within each data set. And so I think this comes back to the fact that when we talked about for the condition changes that you see between query and references, there will tend to be a particular VPR method that's going to be the best for that condition change. And in each individual data set, you actually see a relatively constant change between query and references. And so it makes sense that there is a dominant pair selected for each individual data set. However, I must reiterate that our method can actually dynamically select these pairs without knowledge of which data set it is in, and it was performant on unseen data sets as well. And so that brings me into my third contribution throughout this thesis. So in this third contribution, what we actually wanted to do is focus on modulating the sequence length we use in VPR, all with the goal of consistently exceeding a minimum performance target. And so there's a bit of a 3-part motivation to this. So over the next few slides, I'll try and explain that to you guys. So as I mentioned earlier, VPR research often focuses on the best performance on average across a single or series of data sets, using things like precision, recall, and recall at 1. And I also talked about in practical applications, there are often other equally important metrics that you should be considering. And so specifically for this contribution here, what we wanted to focus on is the fact that during deployment, it is important to consistently maintain above some minimum performance level throughout your environment. So rather than having a VPR method which is performant in, which is extremely well performing in 3/4 of the data set and very poor performing in 1/4, you want to just make sure that you at least maintain your minimum performance standard throughout your entire data set. And how we can usually do this in VPR is introducing approaches like sequence matching, where we improve the general robustness of the approach. But typically in research, we don't consider the fact that the sequence length for successful VPR can actually change quite widely from query to query image. So in the bottom left-hand plot here, you can see an example of this, where the x-axis is the query images, and then the vertical or the y-axis is the sequence length required to actually be successful in VPR. And so in practical applications, the obvious solution to this, where you might just set an overly long sequence length to account from it, can have these unwanted consequences such as increased computation and increased localization latency. And as a little bit of foreshadowing to something I'll talk about later, this is actually not always guaranteed to improve the performance. Now the third motivation that I'll talk here is a bit of a sort of practical consideration. So often in deployed autonomous vehicles, they have access to multiple different positioning sensors. So things like GPS, IMU, LiDAR, and you might have access to all of these. And in these systems, VPR is often used as a bit of a supporting positioning system for when localization via these sensors becomes either uncertain or fails. And this can occur in situations such as tunnels, cityscape areas, or dense forests. However, even though they might not be able to provide a fine-grained localization, we can still actually get some coarse or uncertain position priors from this data. So one of the good visual examples I like to use is that if you're looking at Google Maps or something on your phone and you're in a city and it can't get good connections to satellites, you'll get the big blue ring, which gives you an approximate version of your location, but not necessarily a pinpoint accurate one. And so what we actually want to do is combine all of these with the ultimate goal of allowing the VPR method to consistently exceed our nominated minimum performance. And so we want to combine VPR and coarse position priors to modulate VPR sequence length towards this goal. Now, a couple of the sort of, I guess, hypotheses that we have with this work, or started with this work, is that we think the VPR sequence length is at least somewhat related to the change in appearance you see over consecutive images. So if you're seeing a minimal amount of change across consecutive images, you're probably going to need a longer sequence length to actually account for that. And then, sort of tying into the overall theme of this thesis, we want to use the existing VPR place representations to capture this change in appearance, which will then hopefully dictate the sequence length that we need to be successful in VPR. And we actually see in this work the return of our friend HybridNet from the first contribution for its spatially related features. So once again using that viewpoint dependence that it has to capture this appearance variation. And so we end up with this general methodology that we use throughout this work, where we use a coarse position prior to retrieve a set of reference images within the vicinity of your robot or your platform. And then we're able to use the VPR feature vectors from HybridNet to quantify this appearance variation that we see across these reference images. And so for a feature vector like HybridNet, which might be 4096 dimensional, we actually measure the variation in each individual feature index. So you end up with this appearance variation vector, which is the same length as your VPR feature vector. And so we use this as an input to train a small multi-layer perceptron to dynamically modulate sequence length based on this vector. Again, all with the goal of consistently exceeding our minimum nominated performance target. Now there is a few different components in the training pipeline that allowed us to be able to do this in this research. So this is a bit of, I guess, the general methodology and the approach. So for a given training set, we actually separate this data set into what we refer to as different chunks. So you can sort of see in the bottom left hand here. And each of these chunks in the right hand plot actually represents a particular point or a dot on this plot. And then, of course, we want to actually set our minimum VPR performance level that we want to maintain. And so this actually becomes the dotted line in the plot on the right. And so now that we have these data points, we need to select, or we need to derive a training signal and an input signal to train our multi-layer perceptron. For the training labels in each of these chunks, it becomes the minimum VPR sequence length required to exceed our minimum performance target. And so this represents the X position of each of the dots on the right-hand plot here. And then the input signal for each of these chunks becomes the appearance variation across all the reference images inside that chunk. But we do introduce something else to sort of, I guess, improve the input to our network even further. We introduce this feature curation step, which is sort of starting to pop up in some more VPR works now, where we actually curate or select features from our input vector that are correlated with the specific output that we want. And so for us, this is correlated with the sequence length that is going to allow us to exceed the minimum performance target. And so this correlation is based on an adjusted mutual information score. We use this score because it's got some intuitive values like correlation values that are less than 0 actually indicate that a data point is less correlated than expected by random chance. And so we expect these to be particularly harmful to our predictions. And so once we have our appearance variation vectors, which are 4096 long, what we can actually do is analyze the correlation of each of these feature indices, which is represented in the x-axis in this plot, and then we just set a threshold and we say we only want to take features that exceed a particular correlation. And once we have these inputs, we can start to train it towards this goal of exceeding our minimum performance target. Now, to help it do this, we introduce the use of a leaky ReLU activation in our mean squared error loss term. And this allows us to separately control the penalty of over and under prediction of sequence lengths. And so this is because in the VPR context, we expect that it's better to over-predict a sequence length and likely overperform than it is to under-predict and definitely underperform. In this work, unfortunately, like the sort of previous contribution I talked about, we did have to train a MLP for each individual data set, but we sort of improved the utility of this by using the minimal amount of calibration data that we could, where we take the first 30% of a data set as training data and the last 50% as test data. In terms of metrics, what we're actually looking here is we do still incorporate the sort of standard metrics that you see in VPR, but we look at the recall at 1 on a chunk by chunk basis. So in the plot on the sort of right hand side here, each of these bars represents a particular chunk, and then its vertical position represents the recall at 1 you achieve for queries within this chunk. And then how we introduce the idea of functional metrics into this is we actually want to maximize the percentage of these chunks that exceed the minimum performance target. And we want to do all this at the minimum sequence length possible. And towards this goal, we actually look at the median sequence length of our approach. And so the results of this, where we're comparing to a fixed sequence length across the same data sets, were very good. So if we look at the plot on the right-hand side here, what you'll actually see with the blue line here is this represents essentially the operating curve for a set of fixed sequence lengths. And our approach actually is the green point on this plot here. And because we lie above this operating curve, we can say that our system of dynamically modulating this sequence length is performing better than a fixed sequence length. And sort of how we can sort of explain this is if you look at the oracle comparisons. So for example, if you take the median sequence length of our approach and you match this to a fixed sequence length, our approach produces this green bar plot on the left, where we consistently exceed the minimum performance target in a higher percentage of these chunks than using this fixed sequence length. And then the complement result to this, if you take the fixed sequence length that exceeds the minimum performance target in the same percentage of chunks as our approach, we use a lower median sequence length across the data sets than a fixed sequence length would. Now I wrap up this bit of work again by talking about some of the interesting findings. Now I did a little bit of foreshadowing before, saying that we did provide or see evidence that longer sequence lengths are not always going to be better. And so this is done on the bottom left-hand plot here, where the x-axis represents the sequence length and the vertical axis represents the recall at 1 performance, and each line represents a particular chunk in the data set. And so what you can actually say is there is actually a bit of a plateau before when you're increasing sequence length, you actually see a drop-off of performance. Now the other important result that we found in this is that state-of-the-art VPR methods are not always going to be best or better for specific tasks. And so I actually did do some testing with this approach using approaches such as NetVLAD and SALAD, which are typically considered better performing VPR methods. but they didn't perform as well. Now this can actually be down to the fact that both of these methods use a feature aggregation technique on the end of their feature extraction, and this sort of removes all the spatial relationships between your features, and so you're not actually able to look at the appearance variation across consecutive images in this sort of coarse prior that we're using. And with that, I'll start to wrap up and talk about some of the sort of conclusions and what I hope is the impact on the field from this thesis. As a little bit of a summary, I talked about our first contribution where we used VPR to improve semantic segmentation in challenging conditions through the use of this idea that we can retrieve similar places to use as a prior in a Bayesian update for segmentation. The second contribution, I showed that we were able to improve the sort of functional utility of the existing multi-process fusion approach, reducing the computation requirements and increasing the adaptability through the use of VPR place representations to find complementary VPR method pairs. And then the final contribution I just talked about, we use the place representations to modulate VPR sequence length, all with the goal of making sure we consistently exceed our minimum performance target. Now there's a bunch of different sort of future work that I think we can build off this. One of the things that I think has a huge room for improvement is this similar places idea. I'd be quite passionate for pursuing this because I think there is definitely heaps of room for improvement. And so far what we've done is we've used existing pre-trained VPR methods to do this similar place retrieval, but I think there's plenty of room to train a network specifically for this. And so since that paper, there's been sort of a more wide adoption of architectures like transformers, which actually already incorporate patches and self-attention, which I think would be really useful for the patch-based approach that we used. There's also been papers that introduce things like the generalized contrastive loss, which take a triplet contrastive loss and include a weighting term. Now I think you should be able to use the semantic IOU between different images to be able to weight these images in a contrastive loss. And then in the second contribution, I mentioned that our MLP learned to select 3 of the 9 possible VPR pairs that we saw. And so I think you can improve performance by trying to encourage the network to diversify its selection of methods. And this could just be done in like a loss term or part of the training pipeline by penalizing uniformity of selection. And then in the last work, I think this really opens up an opportunity for a deeper investigation into the effects of modulating VPR sequence length. So some of the things that we didn't get to look at was changing the coarse position prior size or even removing this completely, exploring the training of a single MLP that was performant across multiple different data sets, and then altering more current VPR methods to be compatible. So I mentioned we did some testing with a method called SALAD, which is actually a transformer-based approach. And so I think one of the easy targets for this would be you could take the aggregation step off of this and just use the transformer-based features, with the downside that this would significantly increase the feature dimensionality, but you could get around this by introducing like a fully connected layer to, again, reduce that dimensionality back down. And so with that, I think today I've been able to demonstrate how we've been able to build frameworks and priors around the existing powerful VPR place representations, all with the goal of improving functional performance in robotics tasks. And I hope that future work is able to build off this idea to continue to develop robots that are more robust and adaptable to real-world conditions. Thank you.